everyone. Today we're looking at forces. So let's talk about that. So what is a force? A force is when I would take something and push it or pull it so that the direction or the object starts to move or it starts to stop. So that is of course very just plainly put. But let's have a look. How would we then put a force and draw it in our books? So we're going to use the concept of vectors. Can you remember from grade 10 we said what is a vector? Let's have a look. We're going to say, and we're going to draw it like this. Let's say I do apply a force of 10 newtons. Yes, correct. We're going to measure a force in a newton. And a newton, of course, comes from the name of Sir Isaac Newton, who started all of this. So let's have a look. So let's say I have a force and I'm going to push something in that direction. Let's say with a magnitude of 10 newton. Then I'm going to draw it with a mark like that, starting with a dot. And I'm going to draw a line exactly. Let's say this is the direction of, or the magnitude is 10 newton. I'm going to write it like that. And I could now even do it graphically where I would measure this, let's say in 10 centimeters. And then I would say, okay, I've got a scale of 1 centimeter equals 1 newton. Alright, so if they would want you to draw it by scale, you can do it like that. But then there's something missing, and what is that? The direction. So we're going to put an arrow for the direction in which that force is operating. So that is what we call a vector. So a vector is, of course, where we say something has got a magnitude and a direction. What is, of course, again, a scalar? Can you remember from grade 10? A scalar is when there's only a magnitude and a unit, like for instance, time. Time doesn't have a direction, okay? So we're going to just say it's a scalar. It's 10 seconds, but there's no direction involved. But if I look at forces, there's always direction involved. So of course you could say this is east, or you could say to the left. But we could also use, of course, our Cartesian plane and say, okay, if that vector is in that direction, and we draw it in a 10 newton, then you can remember that we're always going to measure direction from the zero plane. Or we could say, of course, north, east, south, and west. And we're always going to draw in our direction in a clockwise direction from the 0 degrees plane, which is north. So we could now say that is also a 10 newton 90 degrees. Or you could say that is 10 newton on the x plane in the positive direction. So as long as you always give a direction, otherwise you're not going to get a mark for your answer. So it's always a magnitude, unit, direction when we talk about or drawing a vector. Now I'm going to specifically for today only concentrate on forces, and in grade 11 and grade 12 that is what we're mostly going to concentrate on. We will talk later a little bit about acceleration, velocity. They're all also, of course, measurements of vectors. So all of them has got a direction. But let's go back, of course, to our vectors, our forces. Now let's say I have a force of 10 newton in direction. So I've pulled you with a force of 10 newton. And I continue and I now use a force of, let's say, another 5 newton, but in the same direction. So how will we calculate the net force? In which case we're going to call it the resultant force. So we're going to say, okay, I did pull you with a force of 10 newton, 90 degrees. I apply a further 5 Newton. In the same direction, 5 Newton. So what will be the effective or the resultant force on that object that I put that force onto? Okay, so we're going to say, okay, now mathematically, of course, we're going to just add it because it's in the same direction. The arrows goes in the same way. So my resultant force, and I'm going to use force F with capital, and I'm going to say, okay, that resultant force, F resultant, equals then that 10 Newton plus the 5 Newton, which would give me then 15 Newton in a 90 degrees direction. There you have it. So that's easy when they work in the same direction. And we would always say when two forces are working in the same direction, they will have a maximum resultant. Alright? For instance, let's now say I don't apply that 5 Newton force in the same direction. Let's say it's two of us. Let's say it's your suitcase that you take to school with you, or your backpack, or whatever. And you would pull somebody, a friend would pull you towards that side with 10 Newton on your backpack, and I would pull you in this direction, completely opposite, 5 Newton in the opposite direction. So what would be the effect or the resultant of those two forces acting together? Now if we look at that, now of course the moment whenever we do physical science, the moment we have an opposite direction, we're going to use a negative in front of the value. So we're going to now say, okay, the force resultant, or the net force, is going to be that 10 Newton. So I have to show it, I choose as my positive direction. So I'm going to say that direction I'm going to use as my positive. Then if this is working in the opposite direction, I'm now going to put in front of it a minus 5 Newton to show that that is actually what we're saying. Sorry, let's correct. I actually say it's 10 Newton plus 5 because a resultant force is always the sum of all the forces working together. And the sum is of course plus. So I'm going to say plus, but I have to show that this vector is in the opposite direction. So actually I'm going to say 10 plus minus 5. I actually don't have to use already the units in here. And what would that be? So my net force or my resultant force will be 5 Newton. And because I have a positive here, can you see it's a positive answer? I know it's in that direction. So, of course, it's in the 90 degrees direction. Okay, not Celsius, sorry, 90 degrees direction. Now that's easy, easy peasy. So I either add or distract when I get to my resultant force of two forces working on the same point. What if they don't work? Just like left and right or up and down. What if I get them now with an angle? Let's have a look. Ah yeah, if you hear any snoring, it's my dog laying over there, and of course he's not interested in science. Lucky him. No. I'm completely wrong. I love science. Science really makes me tick. And I know it's going slow, but you know what? We learn one step at a time, and when you look back, from here to there, to the end of matric, you're going to really have so much knowledge and start to enjoy the subject so much more because then everything starts to make sense. So just keep in there. Just keep hanging. Alright. Now let's say, we're just going to ignore the phone as well. Let's say we have now two vectors working at an angle. Now let's just start with the easy one, where they work at a 90 degrees perpendicular angle. So let's say I've got my 10 Newton working in a 90 degrees direction. Pulling on that backpack, we can say it again, we can use that as an example. Because one thing you must know what a vector is. It's something real that I'm trying to draw or put on a paper. So that's why we use vectors. Alright, so we're going to say, okay, that is the magnitude 10. The unit is Newton, so I know I'm now drawing a force. And I'm going to show the direction in which that force is working. Now let me put another one. Let's say now you don't pull in the opposite side. Let's say I'm now going to pull upwards 5 Newton. What would now be the net force working on that backpack? Now what we could do, there's two methods. We could either do it like this, and I'm now going to draw from here to the opposite direction, diagonal to where that line and that line is meeting. And the moment I do that, I have my resultant force. Because just try it, huh? Just one pull towards this side, one pulls towards that side. Where is your backpack actually going? It's going right through the middle. I call this the ketty method. I'm sure you all grew up with ketties. Is it the right word in English? I'm not sure. You know, where you would have such a sling, you pull the sling back with a little stone in it, and it's got like a V made of wood. So you pull the elastic backwards with a stone in it, and it shoots right through the middle. And this is exactly what we've got here. So let's say, there's my blue pen. Oh, let's use this one. So that was the two forces acting on the same point. So that will be the resultant force or the net force. But I could also do it in a different way. So you could either then also have your two more vectors here, 5 there, 10 there. And now what I could do is I could say, okay, I'm going to move this one and I'm going to draw it over there. And the moment I do that, I want to tell you something. I can actually pick up a vector and add it somewhere else. As long as it's got the same magnitude and the same direction, I could actually take that 5 and draw it there. It's the same vector. So what we're now going to say, we add them. They're working in the same direction. The arrows are chasing each other. That means they're working first the one and then the other. In that case, actually, you could see they're working at the same time. But I could now just work with this. So I'm going to take that vector and put it right there. So then I'm basically just working with that triangle. And if I do that, I can again then say, from the start, straight to where the arrows are finishing. And then I draw my resultant vector, is there straight from the beginning, straight to the end. So that is your resultant. And then of course you can use your Pythagoras. And you can say, okay, if that is a 90-degree angle, this is 10 and that is 5. And I could now, of course, either do it graphically, where I use a scale, and I physically draw it according to scale. And then I could again go and measure that, and then work backwards with my scale, and I could measure the angle there. Alright, but there's also, I have to then calculate it by using vectors. Then what I'm going to do is I'm going to say, okay, let's use Pythagoras, which would say my F resultant force, quadrat or square, is going to be, let's say I call this my F1 and I call this F2. So it is going to be my F1 square force plus F2 square force. So I could then say, okay, that would be the plus 5 squared, and I can work that out. And let's see how much that would be. Okay, so that would be 10 plus 25 and that gives me 11.180 Newton. But my problem is now I only have the magnitude. So how am I going to know what the angle is here between that either the x plane or the y plane, as I am now working in this triangle, I'm going to use that as with my relative to my x plane. Alright, so how am I going to do that? And now I'm going to use my trick. Okay, so what is this? This F1 is adjacent, F2 is across. So what would that be? I'm going to say, okay, adjacent and across, that is going to be tan theta, which is across 5/10. What am I going to do now? So theta is going to be 5 divided by 10. That gives me the value of 0.5. How do I get my tan to the across? I'm just going to say shift tan. So now I'm going to put into my calculator shift tan, and the value of 0.5 equals, and I get that, so that would be tan -1 or shift tan, and I get 26.565. So what I'm now going to do is I have to make that 565, I'm going to make that a 57 degrees. But the moment I have an angle, I have to say relative to what? I mean 26 degrees from where to where, you know? So you have to now say 26.57 degrees, and I'm going to say relative upwards from the x-plane. So I could say upwards from the positive x-plane. Or I could say minus 90 degrees, which is maybe easier, and I just have to say there in my answer 11.15 Newton, and the resultant force is in the direction, and then I'm going to show this angle. So from the 0 to there, so I'm going to say 90 degrees minus this, so 90 degrees is that full angle, minus that angle, and I'm going to show that one, which then gives me 63.44 degrees. And there I have my net resultant force of those two forces working. So what is a resultant? The resultant force is that one force that has the same effect as any other amount of forces working together. Alright, so that is just now two forces working on an object. Now let's have a look at what would hold those two forces in balance. What if I don't want that backpack of mine to move? What would you then have to do? So there's two guys pulling on your backpack. One with an angle in that direction of 10 Newton, one with 5 Newton upwards. So your backpack is going to move in that direction. Now what do you have to do to keep your backpack from moving? What you will then have to do is you will have to apply the same net force as the resultant, but in the opposite direction. And you're going to pull that your equilibrant. That means that will be the equalizing force. It will hold that backpack still. So it's going to balance out the resultant or the net force working in your backpack. So you're going to be the balancing one that says, no, I don't want my backpack to move. So an equilibrant is always the same. So let's say I forgot now what it was, but let's say we did get our F resultant, we worked it out, everything. So then we know that to balance that force out, I'm going to have to apply a force with the same magnitude but remember now with the opposite direction. So now I would measure all the way around to there to get the direction of that net force, or I could measure it, let's say, and say, okay, but that, where am I now? That angle and this angle is the same, so let's say we're going to just add 100 and 270 degrees minus that angle, and I would get that angle. So just important always to say your magnitude, your unit, and your direction. So this is for two vectors working onto the same object or to the same point. So we're going to always add or subtract, and when it works with an angle, we're going to say, okay, let's draw those two forces, and if it doesn't have, let's move one more, a little bit more difficult. What if those two forces are not working perpendicular? Okay? If there's two forces and they don't work perpendicular, let's say that's the two forces. So it's a 10 Newton force and let's say also a 10 Newton force, and they work with an angle of, let's say, 35 degrees. Now how are you now going to get the resultant force? Now what we do now is we say, okay, that one, so we're going to have to draw it. We can first start with that one and we do it graphically. So I'm going to measure it and put it to centimeters. I'm going to then use that angle from here. So I'm going to have that one, I'm going to put that one, move it to the okay, so I've shifted it, and this one now works here with an angle of 35 degrees. So I just lifted it from there and I moved it to there. So what will be my resultant force beginning straight towards the end, and that would be my F resultant. Now in this case, guys, what we're going to do is we are going to use the sinus rule. Now I don't want to go immediately into that. Let's first see how can we do more than one which works at an angle and still get the resultant force of all of them. But for now, let's stop there. That will be my next lesson. So just keep on focusing, believe in yourself, you can do this.